Well, now it gets interesting because now we're getting to fluids. So let's have a quick look at how it works. Well, how it works in the plane editor. We can do a little swooshy swoosh here, and we get all the nice twirlies and all the nice curlies, and we get some sort of buffers down here. So let's have a little talk about how these fluids go. I'm going to focus on this rightmost buffer right now. You can see there is definitely the pattern from up here, and then there is some red and some green. So let me just explain that in Photoshop. So for every pixel, and this is just some pixel. So for every pixel, I just need some pixel here. This is a pixel. So for every pixel, we have well, we have 3 channels, right? We have red, green, and blue. And we previously looked at how we can store gradients in red and green, or how we can store UV coordinates in red and green, but we can also store velocity. So basically, our G equals velocity, and blue is just a color so we can see what's going on. Blue equals color. Yes. So that means that every cell has a velocity. It means it wants to go somewhere. So let's say, for example, that this cell has a velocity going this way. So that means that we want to move this cell per iteration. The next time want to move this cell, next iteration, pause. We want to move this cell, next iteration, over here. But we can't. We can't because, remember, we cannot go and put a pixel somewhere else. We're processing this pixel. So what we're doing instead is that we take the velocity and we look backwards. And so we find this cell over here, or maybe we don't find exactly that cell, but we find somewhere within it. So like So what we're doing instead of trying to move a pixel forward is that we try to ask, well, what would come here when we have moved away from here? So we look backwards. And so if we look backwards, you can see we find some position here, and we can sort of assume that this one would be going sort of in this direction. So let me just draw out that pixel. So the pixel like this. So this value would then come here, and then down here, another value would sample here. And that can create some problems. For example, like up here, we're thinking that it would be going this way, but I mean, this pixel might really be wanting to go this way. And in the same way down here, this fella might just not be going anywhere. It might not have any velocity, might not even have that. It's just dead in the water. And so you see now we have a problem, because this one will try to go up here to get a value, and so this value here will move down here. But this one is not going anywhere. So even though this one has a velocity, it just stays dead in the water. It hits a wall here simply because this value doesn't have anything. So we expect a sort of continuity. So let me just draw that up like an example of what we would actually be doing inside Unreal. Because in Unreal, when we click and drag, we put down a circle, and the circle has a direction. And that's every pixel in the circle has this direction. And if there's nothing else moving at this point in time, well, then there is like there's a point here where it's just zeros over here. There's nothing going on. And so there is a pressure front right here. So you could say that right there, there is motion. This agrees with this, and then this and this. So all of these simultaneously will agree on that there's a motion going this way. And all of these will agree on that there is absolutely no motion whatsoever. But in between, there's like a buildup of pressure. And here behind, because here there are also zeros, there's like a drop of pressure. We call this the divergence. And the thing is, divergence, or this pressure compression, it doesn't really happen in water under normal circumstances. So you would usually, if you imagine that you have a big container here of some sorts, of some dimension, and you just get rid of these guys here. If you have this big container, you're sort of expecting that this would go this way, and then it would sort of like start diverting, and then it comes around, and then it goes back here. And so there is this idea that you can't just push and get a compression. It will then make this go forward, that'll 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 probably get over here, and then over here there almost be a compression. And so to avoid that, that will also start going in these directions. And so because water is incompressible, it never has this divergence. So we need to solve the divergence that we get, and it gives two things. It gives the swirly whirlies, which we like so much, and it also makes sure that we don't get this where one pixel has a velocity in some direction, and then the next pixel just goes, nah, you're not going anywhere. So removing divergence as much as we can is a very important step. So let's just reiterate what is meant by divergence. So for any pixel, for any cell in our simulation grid, we look at the velocities in the surrounding, well, we're going to use the immediate four neighbors. So this is von Neumann. Like this. And they're going to have some vectors. It might be like one is going here, and one is going here, and one is going like maybe also a bit like this, and this one is going straight up here. And so we want to look at how much flows in and out of this center pixel. So this means, like, for example, if the divergence is 0, we would see that maybe it's flowing outwards vertically, and then horizontally it's flowing inwards. Or maybe it's just that it's flowing through all in the same direction. Like there's nothing going in that isn't, there is not as much, there's not more or less coming into the cell than there's going out. Whereas you can have positive divergence if you find that there is more coming into the cell than there's going out, and a negative divergence if it's the opposite. So looking at this pixel here, the way we calculate the divergence is that we look the neighbors horizontally by themselves and vertically by themselves, and what you look at is the horizontal component, which is x or u, and for these the vertical component, which is y or v. So for this one, for example, the vertical component would be like this, and for this one it's literally all of it. And for these two here, there is the horizontal component going like this, and then a horizontal going nowhere. So let's say we take this one and we subtract this one, and so it becomes nothing minus this one. So it's nothing minus this right going equals left going. And remember that there's a positive and a negative direction. So it becomes minus the length of this. So we get, let's say that this equals to minus 0.6. So we get minus 0.6. And then for the other direction, we take this one and subtract this guy down here. And so it becomes this not so big one minus the somewhat bigger one equals to going a little bit in the other direction, and again negative, so let's say it's negative dot 2, minus dot 2. That's not a 2. Minus dot 2. So that gives a total divergence of minus dot 8. And so this is the way we calculate it for all the pixels, and we get a value for how much do we have liquid flowing into and out of a point. So the way we actually calculate the divergence-free version of this field is actually not trying to do anything with the vectors to start with. Instead, we try to take the pressure that we have found with the divergence, and we try to figure out if this pressure was spread out, so to say, was uniformly distributed. So you get this where there's no one place, there's much more pressure than anywhere else. What sort of pressure field you would then get? So let's imagine that we're cutting through here. And so we are looking at the low pressure back here. And we are looking at the high pressure in the front here. And let's draw this as a pressure curve. So with this cut through, we first start with absolutely no motion whatsoever, so there is no divergence. We then have a negative divergence here because we have more flowing out than we have flowing into the area back here. So we see a dip. Then we get back to no divergence because in here there's as much flowing into this point as there's flowing out of it because they're all going this direction. And then we have the pressure front here, the pressure front here. And so we get high divergence. And this is very much like there's no doubt that there's happening some sort of compression here, right? There's a high pressure here. It's almost like jelly in a way. And so what we want to find out is we want to find out a version of this where there are no sudden rises and no sudden falls. So we keep track of these local changes. We note that this one has gone down, and we note that it's gone up over here, like that we have a negative divergence and a positive divergence. And then now we try to find a field that has as little other, let's call it curvature. It's not the correct term, but like little other curvature as possible. So what we'd end up with is something along the lines of maybe this coming in here, and then it's just going in a straight line over here, and then it's sort of like falling off again somewhere over here. Let me draw that in a different color so we can see what's going on. So we'd get like maybe something coming up and then something going over and then something falling off like this. While the black is our divergence, we should see the green as our actual pressure. And the difference being that the divergence is just a local information about compression and expansion, and the pressure field is where we're actually solving for what is the realistic pressure outcome. And the way we achieve this is that we take for every pixel, so that could be, for example, that pixel, we take the neighbor pixels, and then we average these pixels, and then we subtract the divergence, and then we divide it all by 4. So what we're doing is that we are constantly taking a blur, and then we are constantly counter-adjusting the blur with this local change in pressure. And then what we're doing is that we're dividing it out with enough to get a convergence, not divergence, convergence to this point where we get the green curve, the pressure curve. But you can just think of it as we are sort of anchoring these points, and then we are smoothing out anything that doesn't have any sort of anchoring value. It's not the correct way to think of it mathematically, but it's just an easy mental image to keep track of what's going on. So what does this pressure field actually represent? Well, it basically represents a field where we have our high pressure, where we found our high pressures before, and our low pressures where we found our low pressure, but we have it with the minimal amount of change, sudden change. We call it energy minimization, that we possibly can get away with, or that we, within our computational restraints, can get away with, because we do a very incomplete version of this job. And so if we can then take this and we can sort of find new velocities for this pressure, so like the velocities for this pressure to start dissipating out, and we subtract that from over here, then basically we found the field for then creating all the pressure to not just have a high pressure right here, but for slowly having a dissipating, or more like building up, if we're going this way, of high pressure up to here, but with none of this like hyperlocal compression. Now, of course, this is not what we want. What we want to figure out is almost the exact opposite. We wanna figure out how we can change our velocities for the entire field to accommodate this high pressure without having anywhere where there's any like compression of space. We want to make sure that we keep going in the same direction. We want to make our field divergence free. So if we go back to the Sobel operator, you can probably remember that, let's say we had a pixel with a high value and we had some pixels with some lower values around it. We could calculate some vectors for this field. Like for example, if these were dark, and this one, well, it's actually irrelevant what the middle one is with the calculations that we did, but then these are bright, and we could sort of have ourselves a vector going downwards like this, indicating the slope. And we can now do the same thing with our pressure field up here. We can calculate the gradient of it, and that gradient will be the velocity field that we can subtract from our current velocity field to get a divergence-free, that is a compression-free velocity field. And that is where we then automatically, like I said before, we start getting our whirls, because otherwise we'd have compression over here. We drew that some green. We'd have compression over here, we'd have compression in here, or something like this. Is what prompts the swirls to appear. It's basically that it has to sort of go from a high pressure to a low pressure. And it's not very different from, for example, when you think about magnets showing these flux line. It's basically the same thing, is that you have a high point and a low point. And so you can imagine that around here, it is like going down the slope here. Except, like, of course, the slope looks like it's flat, but it might not be. It might have been from here and back to here, right? Because here we're also having a high pressure over here, and a low pressure over here. And so we end up with the same thing, where we then see that there is a pressure drop, which we have now solved for. So it becomes a smooth drop around, and that's where you get your fields. So yeah, that is basically what it is with removing divergence. So I actually show the divergence. I'm showing them in the fields down here, one for divergence and one for pressure. And if we go ahead and play, and we zoom in here, there is this tick box that is only sim on mouse down. And so if I just draw a little bit and stop, and then eject from processing the pawn, and we have a closer look down here, you can see that if we follow the gradient, it will go outwards from the pressure, the high pressure front, which is peeking out like that, and then curving around and creating this spiral-like pattern in the same way as I was drawing it out before. And you can also see that there is some, it's not easy to see from there. Let's see if we can look down on it, that there is a smoothing of the pressure outwards from here. Whereas if we look at just the divergence, that's even harder to see, but it's really local. It's just exactly where I drew the dot. And so let's have a look at how these calculations are done and how the blueprint is set up. There is some reset, there is a lot of construction script and so on and so forth, but the interesting part is really just the do step. So in the do step, here is the first part where we just ask whether or not we are updating on mouse down, which is just, well, if you're either clicking or if we just say that you should still update when not on mouse down. Then we're asking whether or not we're adding source. This means that if the mouse is down, well, then we want to be painting something into the field. And then we go through all the stages that we do on every frame. So we have a number of render targets that we need to pay attention to. We have the color and velocity, where RG is the velocity and blue is just the white color that we put in. And then we have the two pressure textures for the pressure solving. And then we have the divergence render target. So the first thing we do is adding some source, which means that we just take the mouse position and then in a radius around it, we put in blue for giving some white into the color, and then in the red green we put in the velocity that's just calculated from the previous mouse position to the current mouse position. So we're painting in the vectors for velocity for how fast we move the mouse. Then we do a diffuse step, which is not absolutely necessary. It adds a little bit of blurring to the image every frame so it slowly dissipates. And then it takes a little bit of the blue away every time, so that when you paint it some, it will fade over time. Then we do the advection step, where we move forward by looking backwards. Then we calculate the divergence, which means looking at every pixel and then asking by looking at the velocities of its neighbors whether or not there are more or less liquid flowing in than out. We then take the divergence and the two pressure render targets, and then we sort of solve for as divergence-free field as possible within the number of iterations that we do. So we're doing this relaxing / blurring and counter-adjusting step maybe 20, 50, 100, 200 times every frame in order to get as much spreading out and as little divergence as possible in the pressure field. There's a name for this solver. It is called Jacobi iterations, and it's solving a Poisson equation. After this, we calculate the gradient of our pressure field, and we subtract this gradient from the velocities that we have in order to get the divergence-free liquid. In between, because we are as usually using two different buffers to write back and forth between, we're just going tick-tock, which just means we are switching back and forth between which buffer is the one to read from and which is the one to write to. Looking at the materials, we start with the advect. So what we do is that we sample for the pixel that we're currently looking at. We're taking the velocity, we're scaling it down to within pixel space. We are subtracting that from the actual UV coordinate, and then we are resampling the same texture again. So we are sampling the texture, getting a velocity, going against the velocity, and sampling again. That is advection. For the diffusion, we just use the convolute kernel to give a little bit of a blur. You can see down here that we are sampling the texture for the convolution for creating the blur, but we're also going over here and getting the blue because we don't want to blur the blue channel because it'll just take some definition out of it, but we want to blur the velocities. And then we are scaling both the velocities and the blue down with 2% every frame. For fluid source, what we do is that we have two values coming in. We have a direction and a position. So this tells where we are making a splotch, and this tells what direction it's being dragged in for getting some velocity. We calculate a mask by finding the distance to the point from the UV coordinate. We are dividing by the size, clamping and inverting, so we get a white splotch on a black background. And then we're using this mask to first scale the velocities. So we have the incoming velocity, but we don't want to add any velocity if it's outside this mask. And then that is a vector 2, a float 2, so a 2-component mask, the red and the green, and we need to append the blue. So we just append the mask with a lower brightness blue so that we don't way too intense when we're painting. It's just an artistic choice. So we just add this new splotch on top of our existing texture. Then it's the divergence calculation, which is basically split up in these two, where it's the horizontal, the right-left, and the vertical, the up-down, where we sample the pixels above and below, and subtract only the green, that is the vertical component, from each other. And we do the same with left to right and subtract only the red, the x, the horizontal component from each other. And the result we just add together. And that's how we calculate divergence. For the actual solver, it's pretty straightforward. We just have our usual convolute kernel, and in this case we are just using a von Neumann with no center pixel, so the above, the below, and the left and right. We just sum them up, then we subtract the divergence from it, and then we divide by 4. And that's basically all we do. And by repeating this 50 or 100 times, we slowly get the divergence-free field that maintains the local pressure that we needed. Once we have removed divergence from our pressure field, we then calculate a gradient in here. You can see it's much simpler than the Sobel operator. We're just using the von Neumann diamond shape, so it's just 4 samples. It's not all the way around actually. And we're basically just finding the difference from the left-right values, between the left-right values, subtracting them from each other to get our x or u component, and doing the same for up-down to get the v or the y component. We're scaling it down, and then we are just using that to subtract from our velocity texture, so taking it away from the velocity. And as you can see, we're not doing anything with the blue channel. And yeah, that's basically how you do fluids. You seed some velocity, you find your divergence, you calculate a divergence-free pressure field, you use that to find a gradient, and you take that gradient, subtract it from your velocities so that you get a divergence-free velocity field, and in that way propagate your liquids and get those nice spirals.